this video, we'll talk about confidence intervals. So far you remember the classical linear model assumptions that we've been using. If those assumptions are satisfied, we are able to construct confidence intervals for the population parameter beta j, right? So any population parameter that we have that is denoted by beta j, we can easily construct the confidence interval for that. These confidence intervals are also called interval estimates because they usually give us a range of values for the corresponding population parameter. Okay, so typically we would write out our confidence intervals. There's going to be an upper bound and a lower bound. So we're going to say beta hat j, whatever our estimate is, minus c times the standard error of beta hat j. Okay, this is our lower bound, and the upper bound is just going to be this expression. Instead of the negative sign, you have the plus sign. Okay, so you're going to have an interval of this sorts. Okay, so this value of c is basically going to be chosen based on some sort of a confidence level. Okay. So it's important for you to know what these mean. So when we say that we are constructing 95% confidence intervals, we are basically saying that for 95% of the random samples that we draw from the population, the interval that we compute using this rule that we just specified will include the value of the population parameter beta j. Okay, so even though we are constructing this confidence interval using one particular sample that we have, we are not talking about the value of beta j lying in that interval for that sample. Okay, so we are talking about for all of the random samples that we would draw from the population, 95% of those samples would contain the value of beta j. Okay, and this is very similar to the idea of unbiasedness that we were talking about in previous chapters, where we said that the unbiasedness of our estimator does not mean that beta hat j is equal to beta j. And it also does not mean that most of the time beta hat j is equal to beta j. It just means that if we had repeated random samples, right, if we carried out random samples repeatedly and took a lot of random samples and we tried to look at the average value or the mean of these beta hats, that would equal what the value of beta is in the population. So typically, for any confidence interval that we have constructed for beta j, we can test any null hypothesis against a two-sided alternative, right? So let's say the hypothesis is that beta j takes the value of aj, and then the alternative is that it is not equal to aj. Okay, so the first point here is that if aj lies in the 95% confidence interval, then we fail to reject the null at the 5% level if we are testing at the 5% level. And second, if aj is not in the 95% confidence interval, then we reject the null hypothesis in favor of the alternative at that level. Okay. And remember that whenever we are talking about significance levels and confidence levels, these are two sides of the same coin. Significance levels, when we say we are testing at 5%, then we are necessarily talking about a 95% confidence level. Okay, so If you know one, you can discern the other. Okay, so let's take an example here. Let's say that our 95% confidence interval for the effect that IQ has on wages lies in this confidence interval. Okay, so this is the confidence interval. And if we wanted to test this hypothesis, which says that there is no effect of IQ on wages, then notice here that we can reject the null against the two-sided alternative at the 5% level, okay? Because the value of 0 is not contained in this interval. Okay, similarly, if we wanted to test this hypothesis, which says that the value of that population parameter for IQ is equal to 0.01, then we will have a hard time rejecting the null, right? Because this is the value 0.01 actually lies in the interval.